The coefficients BI are the feed-forward coefficients and the AI are the feedback coefficients. Xn is the audio input signal and Y of n is the output signal of the filter. Because of the feedback path, the IIR filter can start to oscillate and even to become unstable. And this happens if the poles of its transfer function in the z-domain are outside the unit circle. But when the poles are just inside the unit circle and close to it, this filter produces an impulse response of decaying oscillations or sinusoidal signals. As an audio signal, this can sound like a tone from a bell, for example, and in this way it can be used to generate a signal. So the corresponding difference equation in the time domain is given here by this equation 1, and we have our output, we have our input, we have our B coefficients, and we have our A coefficient. You can also take a look at the book by Oppenheim, the discrete time signal processing, on chapter 6 from the 1989 edition. Then when we take the transfer function of this difference equation, so the resulting transfer function in the z-domain, you can also take a look at the lecture mentioned here. So in order to understand difference equations and also the transfer function in the z-domain, and this becomes the resulting transfer function is given here. For our test generative example, we would like to have a decaying sinusoidal function as an impulse response. And we obtain this from a simple second order IIR filter with the B0 equals to 1 and 0 elsewhere for L equals to 1 and R equals to 2, meaning just two feedback delays and coefficients. Then we have this equation number 2 here. So we are setting B0 equals to 1, 0 elsewhere, L equals to 1, and R equals to 2. And the resulting transfer function in the z-domain is then given here. And now we notice very interesting things here. The denominator polynomial is of order 2, and hence it has two zeros, which result in also two poles, P0 and P1 of the transfer function h of z. Each pole causes an oscillation at a frequency which is given by its angle to the real axis in radians, where pi is equal to 180 degrees, interpreted as normalized frequency, where 2 pi corresponds to the sampling frequency. If we want a real valued oscillation, we need a conjugate complex pole pair. So let's try to look at an example to make it a bit more practical and to understand a bit more the theory. What we want is that we want a decaying oscillation as an impulse response with a frequency of 440 Hz, which is a musical pitch A, at a sampling frequency of 8,000 samples per second and a decay factor of Q equals to 0.995%. So the normalized frequency will be then 2 pi times 440 divided by our sampling frequency divided by 8,000. And then we'll have the conjugate complex pole pairs given by Q, which was calculated here, times the exponential of plus or minus j, the imaginary number, times Q. So let's use Python to have these poles. So I'm using a NumPy for mathematical operations and pyplot, matplotlib for plotting. So we are defining our Q, because in here is part of the formulation of our problem. Then we are calculating omega. It's given by this equation here. And then we have our conjugate complex pole pair given here with plus or minus j times q exponential. And then just using an interesting approach from matplotlib to plot the unit circle, and also having here the complex z-plane with the real axis and the imaginary axis. And we have here our poles. They are symmetric. They are, because they are, of course, as defined here, conjugate complex. So with these poles, the transfer function now will become this equation given here. And we have here now, we have our poles P0, P1, and when we compare with the formula of our transfer function in the z domain, and we can see that A1 is equal to adding the poles, and A2 is a multiplication of the poles. If we use the above pole pair, and reminding the Euler's formula that e to the power of j omega is equal to the cosine of omega plus j times the sine of omega, and this becomes A1 is 2q times the cosine of omega, and A2 is minus omega squared.